And so we are getting started with the 10th edition of this meeting. It is rare to get anything to 10th edition at IIT Madras. So therefore it's great. It gives me a great happiness to get this started. Today's first speaker is Srinivas Rao Bakshi, and we will have him speaking for 30 minutes. So I will give you a warning at 20 minutes, then another 5 minutes you can speak, and then 5 more minutes for questions. That is the whole idea. And you know, it's a multitude of people, as you know, so therefore it has to be effectively about some broad themes. I hope everything will go well. Thank you very much. Let's get started.
Okay. Are you able to see my presentation?
Yes, I can hear you.
Okay. Good evening to everyone here, and thank you for providing this opportunity to talk about my research. I'm going to talk about reactive spark plasma sintering, examples and possibilities. And this is an outline because it's a general audience. I'll talk about introduce sintering, hot pressing, spark plasma sintering, and then I'll talk about reactive spark plasma sintering and give some examples from our research, and then a summary. As you know, powder metallurgy is a manufacturing process, and very popular process. It involves preparation of the powder mixture, followed by compaction into the shape that you need, and then followed by sintering. Sintering is a thermal treatment of a porous compact, and it creates bonds between particles and increases the density by eliminating the porosity and increases the strength. For example, if you want a porous compact as well, you have to do a sintering to increase the strength for the formation of the bonds. So this is how the sintering progresses from a porous compact to a dense compact, and this is an example of alumina. And we have several types of sintering. The conventional sintering is basically heating the compact in atmospheric pressure inside a furnace, and this requires high temperatures and a higher sintering time, and this may lead to grain growth, which will reduce the properties. To reduce the sintering temperature and the time, we can apply a pressure during sintering, and that requires a special equipment called as a hot press, and the time which will reduce the grain growth. Here plastic deformation and grain boundary sliding aids the sintering, and the kinetics can be expressed by this equation here. So this is the sintering rate, and this is proportional to the applied pressure, and there is a factor here which is called stress intensification factor, because in the initial stages the porosity is high, the actual pressure at the contacts is higher than the applied pressure, and you have a stress exponent n here, and you can measure these from actual data, and based on the values that you get of m and n, you can actually find out what is the mechanism that is acting. For example, if it is a plastic deformation is the mechanism, you will have a grain size exponent as 0. That means the rate doesn't depend on the grain size, and the exponent here can be from 3 to 10. So it is essentially dependent on the pressure, and commonly used pressures in case of hot pressing is 10 to 50 MPa in case of ceramics. Now, coming to spark plasma sintering, in spark plasma sintering we use a pulsed DC current. So this is the modern spark plasma sintering equipment. We have graphite spacers, a die, and a punch made up of high density graphite. We have powders which is put inside this die cavity, and then we apply high voltage DC pulse. Okay, and the equipment available which can give you 2 to 20 kiloamps DC pulse, and load you can. These pulses are generally for this equipment it is 3.3 millisecond pulse. And you can
Mr. Bakshi,
vary the on and off time of the pulse.
For your voice is coming off and on. Maybe you can switch off your video to increase the.
Okay.
Thank you. Please go ahead. Yeah.
Yes, just stop. Okay. Is it visible, my presentation?
Yeah, all fine. All
okay.
fine. Go ahead.
Okay. So here you can see there's a on time of 1 and off time of 1. Here we have 3 on time, pulse on time, 1 off time. Here it is 12 on time and 2 off time, which is the general pulse rate that we use. Okay, now here what happens is when you pass electric current through the dyes and the powders, you have essentially it leads to Joule heating at the interfaces, and you have a localized heat at the interface and a massive heat. And the localized heat results in high temperature at the interfaces, leads to bonding, and the massive heat leads to plastic deformation, promotes the plastic deformation of the particles. And this differs from hot pressing in the way that in hot pressing, the heat is conducted from a furnace to the die. Here, the heat is produced within the die. And since we are using graphite, we can have very high heating rates in our equipment up to 1000 Kelvin per minute, whereas in a hot press, you can heat the maximum to 80 Kelvin per minute. So the time required is very less. And you have several mechanisms which are active here. For example, when there is a breakage of contact, you have spark generated, which will lead to cleaning of the surfaces, removal of oxide layers, and leads to better bonding. Here is then there are electromigration, electroplasticity, which improve the reaction rates or mass transport rates. Here is an example of a gold and aluminum, which is put together and annealed at 450 degrees centigrade for 4 hours, and without current, this is the reaction that happens. And with increasing current density, you see that there's more and more reaction. So there is a more mass transport that happens when there is a current passes through. So the advantages of SPS is you can do sintering at low temperatures, high heating rates, so the time of sintering is less, so you have less grain growth, less energy sintering. And what we are doing is reactive spark plug sintering, carbon or tungsten oxide and carbon. Several borides, carbides, and nitrides can be produced by the reaction of elemental powders. And we make ZrB2 powder by reaction of ZrO2, B2O3, and carbon. And B4C is produced, boron carbide is produced by B2O3 and carbon. And reaction sintering is basically a process where the constituents of the compact react during sintering to form the desirable compact. For example, you take the constituents of for forming a gas. Byproducts in this, which could be gaseous, or there could be solid second phases, which could be helpful. Borides produced in metal matrix composites are oxided by enthalpy of the reaction. So the reaction leads to release of energy, which is helpful in the sintering. So reactive spark plug sintering is nothing but we carry out this reactive sintering in an SPS. And so now I'm going to talk about what we are doing. And so we have been working on ultra high temperature ceramics, metal and ceramic matrix composites, and high entropy alloys and carbides. And just a small introduction to ultra high temperature ceramics. If you look at the melting point of different materials, there are 3 metals which have melting point above 3000, only 1 oxide. There are several borides, several carbides, and some nitrides. and typically these carbides have high density and are not good, don't have good oxidation resistance. The borides are very good for very high temperature applications, such as this hypersonic scramjet powered vehicle. You have these leading edges which are sharp for maneuverability, and these can go to temperatures more than 2000 degrees. And so you need a very high temperature material for these leading edges, and that is made up of this ultra high temperature ceramics, which is ZrB2 and HFB2, and they are made by powder metallurgy. Now, our RSPS work started with serendipity. We were planning to do work on TI-TIB composites by taking metal and boron and mill it, and then do spark plasma sintering to prepare a TI-TIB composite. And then we tried making TIB2 by heating in a furnace, and then followed by spark plasma sintering. And we found very interesting results. So here is the XRD of the powders after ball milling, and these are Zr and boron, titanium and boron, and then mixture of Zr, titanium and boron in different ratios. And this is after 0.5 hours. This is after 8 hours of milling. And when you do a DSC of this, when you heat it in a DSC, you see that there is a transformation from alpha to beta, and then there is a reaction forming the borides. And this reaction is a exothermic reaction, as you can see here. But when we put it in a SPS and we heat it, we find a very interesting reaction. At around 630 degrees centigrade, we find that there's a spark formation and there's a sudden punch displacement. And after that, there's not much happening. And this punch displacement means that there is a sintering that is happening. This is within actually a few seconds. And these are curves showing punch displacement with time. And this is for a 4-hour milled powder and 8-hour milled powder. And you can see that when we take the sample out and we break it and look in SEM, we find that it's fully dense. And the grain sizes are very small, 1 micron or less high, which means we can actually sinter it. So initially we did it at 1400 degrees centigrade, and since this reaction was happening at 630, then we did at 800 degrees centigrade, and still we found fully dense compact. So this is a very good method for sintering TIB2. Then we moved on with ZrB2, and we did the same milling of Zr and boron, and then subjected to SPS. And at 800, 1000, 1200, and 1400, and as you can see, the density increased with increase in temperature. And what you see is that there is an increase from 76 to 89 or 90, close to 90 at from 1000 to 1200, and that is because of there is an additional densification step that happens at 1200. And if you see here in the structure surface images, you can see that with increase in temperature, there is a more and more densification, and that is due to plastic deformation, plastic flow aided sintering. And so what we did is we kept the temperature at 1200 and we increased the pressure, and you can see that at 1200 degree and 100 MPa pressure, we were able to get fully dense ZrB2. And these are some of the lowest, they are actually the lowest temperature for obtaining fully dense ZrB2. And these are XRD patterns which show that ZrB2 is formed, and the oxide at low temperatures and lower pressures, you have some oxide particles, oxide phases, but at high pressure and high temperature, the oxide is reduced back to ZrB2. And we have also done some mechanisms, studied the mechanisms of this by interrupting the sintering process at different temperatures. So here we are heating to 1200 and holding for 10 minutes. And we have interrupted when it reaches 1000 degree, 1100 degree, and this is at 1200 degree after holding for 10 minutes. At 50 MPa, this is after 80 MPa. This is at 100 MPa, and you can see how the density increases. Similarly for the titanium and boron mixture. And when we see an SEM, we can see these mechanisms of plastic flow aided pore closure, and you can see the formation of TiB2 here by this mechanism, and you can also see the plastic flow by this in further detail the ceramic samples by EBST, and you can show that indeed there is a basal and prismatic slip both happening in TiB2, which assisted the sintering, whereas there is only basal slip in case of ZrB2. So plastic flow is definitely happening, which is assisting this sintering. Okay, now what all can we do with RSPS and what all we have done? So there are tremendous possibilities because of several advantages such as low sintering temperature, fine grain size, low sintering time, uniform microstructure, and unique microstructure that we can get. So we have done several things. We have made titanium carbide with different carbon to metal ratio. We have made titanium matrix composites. We have made max phases. We have made coatings of ZrB2 and ZrB2 SiC composite on an niobium alloy. We have made CNT and graphene nanoplatelet reinforced UHTC. We have made textured UHTC, crystallographically textured. We have used TIB and ZrB as a sintering additive for boron carbide and ZrB2. We have made high entropy carbides by reactive spark plug sintering, and we also made solid. So here is our results on preparation of titanium carbide with different carbon to metal ratio. So essentially, we take different carbon and titanium in different amounts, and we ball mill them, and then we do reactive spark plug sintering at 1400 degrees centigrade, and we are able to get this rock salt type structure. And when you look at the cross section, you can see there is fully dense, and then we have measured the hardness and elastic modulus of these carbide as a function of the C by Ti ratio, and we also measure the lattice parameter, and we can get from the lattice parameter what is the C by Ti ratio using this kind of a graph. So essentially, this is very important because TIC is used as a reinforcement in metal matrix composites, and the properties is highly dependent on the carbon to metal ratio. Okay. Now, this is a very interesting work of graphene nanoplatelet reinforced TiB2. So here what we have done is we have milled titanium and boron first for 8 hours. Then we have mixed graphene nanoplatelet and milled for 2 hours. And then this mixed powder we have done RSPS to get the TiB2 composite. And we find that there is this spark happening in this case, and you have a sudden sintering occurring here up to 4% volume percent of graphene, and beyond that we see a gradual reaction. And there's a very interesting observation we find here is that there is formation of crystallographic texture in the sample when we do the sintering. So we find that there are elongated grains of TiB2 that are formed. There are very large grains formed, which are by templated growth of TiB2 over graphene, and equiaxed grain, which are formed by homogeneous nucleation or by conventional routes. And this actually led to very high fracture toughness, indentation fracture toughness. Okay. So now when you make this RS, there is some oxide phase at the interface, very small amount, and it is very useful for forged. Okay, so we call it spark plasma forging, and after the forging, we find that there is a texture that is developed. You can see here, this is the 001 peak is very less on the, this is the side surface, and on the top surface of the compact, the 001 is very high, and 010 is very low, which means it has undergone crystallographic texturing. And we have measured this Lord-Geering factor, which gives you the crystal is the texture, measure of texture, and 0 means random and 1 means complete texture, and it turns out to be 0.84 and 0.72 for these XRD patterns. And this is before texturing, and this is after texturing. You can see that there is
we have 5 minutes. We have 5 more minutes. Huh?
Sure. So there is a grain growth, and when you look at the EBSD pattern, you can see significant texturing that has happened in this materials. Okay, so this is another example of using the TIB as a sintering additive. So since the TIB reaction is highly exothermic, we can add it as a sintering additive for boron carbide. Boron carbide is very difficult to sinter, requires temperature more than 1900 degrees centigrade by hot press, even by hot pressing. And so what we do is we mill it, TIB milled for 8 hours, we mix with boron carbide and mill for 4 more hours. And then we do a sintering at 1400 degrees centigrade, and we are able to get fully dense for 5% TiB2 addition, and we are able to get fully dense boron carbide. It's a composite. There is a tungsten carbide contamination from the milling, which also helps in the sintering, and we actually get formation of tungsten boride and titanium tungsten boride in this process, and we get a fully dense, almost close fully dense material at 1400 degrees centigrade. So this is a very low temperature method for producing boron carbide composite, for which we have been granted an Indian patent. Okay, so and then I think this is the final slide on the application on high entropy carbides. So we can use, you can take metal and carbon mixture, and then you can ball mill them to intimately mix the carbon in the metal. Then we can do RSPS, and we can generate, and when we do that, we get a rock salt type high entropy carbide. This is a new composition that we have made, and we are able to get at temperatures of 1600 and 1800 degree. This is the cross section of the samples, and there are some TiO2 still present in the sample, and we can see that so our SPS temperatures are much lower than conventionally used temperatures for hot pressing. When you take carbides and mix them and do the sintering, and by reactive sintering we can get at very low temperatures. And our properties, elastic modulus, as you can see, is comparable to many of the high temperature carbides. And here we are able to get these properties without using hafnium. And hafnium is a very expensive metal, so we are able to get good properties even without using hafnium in this case. And so coming to the summary, reactive spark sintering has great potential for low temperature sintering of ultra high temperature ceramics, ceramic matrix composites, high entropy ceramics, and many more systems. It results in fine grained ceramics, and it also results in unique microstructures, and reactive spark sintering aids can be also helpful for low temperature sintering. And the spark plasma forging after RSPS has a lot of possibilities for generating crystallographically textured ceramics. So this, I'd like to thank you. Do you have any questions?
So very nice. We have a few minutes for questions. Thank you very much for giving that time. So let me just start by asking one question here. So the pretty key point here is the time during which, a very short time during which you apply this reactive spark plasma sintering is occurring. Now, when you do this, obviously in a solid, the growth along multiple directions, you touched upon that. The growth along multiple directions have different kinetics, can have different kinetics. So as a result, you can have a specific kind of a crystallographic orientation. You mentioned briefly about that. So if you, I mean, forget about cubic kind of materials wherein, you know, you are expecting things to grow along sort of similar growth rate of same growth rate along XYZ. But how does it happen in is rhombic or something of that kind? Are there specific orientations you can get?
Yeah, actually, what we feel is that the temperature, actually the adiabatic temperature, if you see, is more than 3000 Kelvin for this reaction. So we feel that there is a molten mixture that is formed, which is like temporary, like a very transient molten liquid. And once the reaction happens,
time scale of your spark plasma time scale.
Yeah. So okay, something has happened. I'm not able to see the screen. Okay. So actually, the whole reaction happens in 4 seconds, and the melting happens, and then once the boride is formed, the boride has a melting point above 3200 degrees centigrade. So it instantly, there's a transient solidification also, transient liquefaction, and then instant solidification that is happening. This is what we believe. Are you able to
I
hear
can
me?
I can see, I can hear. But so specific orientations can come in probably other crystal systems.
We found that is true. We found that when we add ZrB2, we get fixed texture. When we add GNP, graphene nanoplatelet, we find texture happening. But otherwise, it is not textured. And actually, for the ZrB2, it is the surface energy is anisotropic, so we can see grains also elongated and so on. But for TiB2, for ZrB2, it is not so. So even though it looks equiax, there could be crystallographic texture present.
So can you get
when we do the forging?
Can you get metastable phases as well?
I think it is possible because the time of processing is very short, and it is possible.
I know we are having some network issues. We are having some network issues.
I mean, yeah, it is possible.
Okay.
Yeah.
Thank you. Are there other questions?
Actually, my screen has gone blank.
I know. It is happening. I think all through there is.
Professor Pradeep, I have some couple of questions.
Yeah, go ahead, Pramod.
So, Professor Bakshi, so during this reactive star plasma sintering, because the time scale is very, very small, okay? So there is a probability of the overshooting of the temperature. Let's say if you are taking 1000 or 3000, so it may go some couple of hundred more and go. So how you get rid of that one, overshooting?
Yeah, so that is true. So that is the mechanism and the time scale is actually not short. Our heating rate is about 100 or 50 degree per minute. And then we heat to 1400 degrees centigrade and we hold for 10 minutes. So that is the process. But the reaction when it happens, that is only for 4 seconds. And most of the sintering is complete in that 4 seconds. The formation of the products and sintering almost occurs at that in that. And actually, and then at high temperature, there is a plastic deformation also that is aiding. And during the reaction, the temperature at the interfaces can go very high. And that's how when we pass current, the interfacial temperatures at the particle interfaces will be much higher than the overall temperature. We are measuring the temperature at the surface of the die and using a pyrometer. So it is actually the die temperature. So, so in that sense, the local temperatures could be much higher, and that is why the reaction kinetics are also very high.
Okay, and another thing is, so what types of a material can you sinter with SPS? We are mostly talking about the ceramic or ceramic nanocomposite, but like any metallic or some other system,
we can,
or any specific protocol you have to taken for different material. Yeah,
we can even do magnesium, which is a reactive metal. We have done magnesium also because we operate at 40 Pascal pressure, and magnesium does not react under those conditions. And we can also do insulating ceramics, aluminum oxide, and so on. So all kinds of materials can be sintered.
And how you decide the pressure and temperature for a particular sintering? Take a phase diagram before, pressure, temperature, phase diagram of that system, and then you
kind of we definitely look at the melting point. And we have data for hot pressing typically available, and we generally use temperatures 200 to 400 degree lower than that, because we know it will work. But it is always a trial and error to obtain the optimum parameters.
Thank you.
Thank you.
Close this here, and thank you, Professor Bakshi. So we will move on. Thank you for the talk. We'll move on to the next talk by Professor Pramod Kumar Naik, and he's going to speak to us on van der Waals heterostructures. You can share your screen, and then usual 20 minutes, and then 5 minutes.
Yes, sir. Yeah. So let me. So Professor Bakshi, you have to sign out. Sorry.
Yeah, just take this out. Just take this out. You can share it also. You can go ahead. I mean, his network is poor. So.
Okay. So let me share the screen. Yeah. So are you able to visualize my screen? Let me.
Not yet come.
Yeah, I'm sharing now. Can you able to?
Yeah, we can see the screen. We have to choose from the view options. Right now, even Bakshi's thing is still operational.
I think he needs to unshare then.
Yeah. Professor Bakshi has to unshare.
It's fine.
No, I can see the screen. I just have to choose it in Zoom view options. I can see that there are both, but yeah, okay, now it's fine.
It's fine now. It's fine. Okay, carry on. Yeah, it's fine. Carry on.
Yeah. So good afternoon to all of you who are present in this meeting. So thank you, Professor Pradeep, to give me opportunity so that to share some of my recent work, what I am doing here. So this topic is a mostly interdisciplinary topic, and the nature of the audiences are also interdisciplinary. So I think you can have some fruitful collaboration after this talk. So first, I will talk about van der Waals heterostructure. So before going to that one, so let me show you that what are the different nanomaterials and their confinement. When you talk about the nanomaterials, so mostly we are talking about the threshold value, that is called the de Broglie wavelength, or the Bohr radius of that particular material. When the sizes of that material goes below the Bohr radius, then we can tell that is a quantum confinement effect, and the nanomaterials exhibit unexpected chemical and physical property. So there are the different types of nanomaterial exist, starting from the quantum dot to one-dimensional material to two-dimensional material. You can see when you talk about the three-dimensional material, so there is no confinement effect here. The charge carrier try to move in all possible direction. But when you go for two-dimensional material, the confinement is one direction. When you go to 1D, so the confinement is along the two direction. And when you talk about the 0D, so all the confinement is along the three direction. So similarly, all the density of states will vary accordingly due to the confinement. So when we talk about the two-dimensional material, so there is a huge class of two-dimensional material we can call a atlas of two-dimensional material. So the first class of the two-dimensional material is called the graphene. So it is a very well-known topic. And the graphene is nothing but the hexagonal network of carbon atoms arranged in a honeycomb crystal lattice, which are discovered in 2004. And if you can take the energy dispersion relation EK diagram, so you can see it is a linear dispersion relation, and the valence band and conduction band meet at the Dirac point. So it is not a band gap material. So it is called a semi-metal. So due to the lack of band gap, so we cannot use to tune the Fermi level of the system. So we cannot use in the semiconductor industry. But for the flexible electronics and some other application, we can do graphene. But for the logistic electronics, we cannot able to do. That's why there is a need for other two-dimensional materials which are layered structure and they are two-dimensional in nature, as well as they should have some semiconducting property. So you can see there is the periodic table where we can see different types of other 2D systems evolve, starting from transition metal dichalcogenides. You can take 4 to 10 elements and you take the combination of chalcogen like sulfur, selenium, and tellurium. You have large variety of materials. Then similarly, group 3 chalcogenides, group 4 and group 5 chalcogenides, which is called the topological insulator. Mostly the physicists explore this material, but the topology is a conductor and inside it is insulator. So there are different class starting from the graphene, from black phosphorus, marcin, hexagon bond nitride, TMD, and so on. So every day, every week, you can see there is another new class of two-dimensional material add up into this field. So there is a huge class of 2D materials. And these materials are called the Van der Waals material because the in-plane bonding governed by the strong covalent bond, whereas the out-of-plane bonding governed by the Van der Waals force. That's why it is called the layered material or the Van der Waals material. When you talk about the conventional semiconductor like silicon, germanium, this is just like a potato type of structure, whereas if you can take a two-dimensional material or the layered material is just like onion or cabbage type of structure. So you can cleave layer by layer, layer by layer. So here you can see a schematic of a TMD MOEC, where the molybdenum atom is sandwiched between the two sulfur atoms. So in plane bonding is strongly covalent bond, out of plane bonding is the weak Van der Waals force. So we can cleave layer by layer, and we can get like single layer or some few layer. And these materials are showing diverse electronic property because starting from the graphene and semi-metal, then you have the insulator like a hexagon bond nitride at the band gap of 6 eV. And in between, you can see the one material from the TMD group, and this band gap varies from 1 to 3 eV. So these materials are very, very interesting because it starts from the UV visible to IR to NIR in this region. So mostly technological range it is covered. That's why it is more interesting than that of the graphene. And here huge potential application of this material. Here I have listed a few. So as it is a monolayer, you can use in display technology. As it is a single layer material, you can avoid the out of place scattering. Then you can have the high mobility. You can use as the channel material for the field effect transistor. Then if you can making a heterostructure, the charge transfer is very high. You can use on the solar cell, and you can use due to the high surface energy, high surface area and high conductivity. You can use for the electrodes for the supercapacitor and the lithium-ion battery. You can use also for the chemical sensor, or you can use for biofunctionalization. You can put some biomolecule seed and you can do sensing. So, and lots of more application I am not quoted here. And so what our group is doing, starting from the material growth and exploring the intriguing physical properties to their application. So mostly we prepare this material such as graphene, TMD, all this molybdenum disulfide, selenide, tungsten bed sulfide, and diselenide we use to prepare topological insulators. And also recently we have started some work on anisotropic TMD, so we can find the different anisotropic parameter of this material. And then we make heterostructure. So when you make heterostructure, there are two things. Either you can go joint laterally, we can have the lateral heterostructure, we can have the Van der Waals heterostructure, one over another, we can put it, we can get some hybrid heterostructure, and then we can rotate one over another. We can call the twisted heterostructure, which is emerging a new field called the twistronics. And we can have different multifunctional application. By using this material, you can have the clean source of energy, that is a blue energy is one of the renewable energy source. We can use for the thermoelectrics, photodetector, and flexible electronics. So all this we are working, but here in this I will talk about only the growth of the TMD and Van der Waals heterostructure as well as the twisted heterostructure. So when you prepare this material, there are two approaches. One is called the top-down approach, another is called the bottom-up approach. In the top-down approach, you take a single crystal, then you take a sticky tape, and then you peel layer by layer and layer by layer. We can end up with a single layer and monolayer. If the bond between the two layers are very strong, we cannot able to pick up using the mechanical exfoliation. Then you can use some liquid phase exfoliation, and also you get some chemical synthesis. But here the advantages, you can get very good crystal, but the disadvantages is the size is very limited. You can get up only few micrometer sizes and is not suitable for the industrial production. Then another approach is called bottom-up approach. What you do, you can use the physical vapor deposition or chemical vapor deposition. Using this, you can use a single layer material first, then you can grow bilayer, trilayer, and top up. So you can bottom to top, you can approach. So CVD is the most prominent technique for the synthesis of this TMD and graphene. So I will elaborate it more. And coming to the synthesis of the TMD using the CVD. So this is a schematic you can see for the CVD setup. So here you have the two zones. One is the high temperature zone and the low temperature zone. In the high temperature, you can put some precursor powder like molybdenum oxide or tungsten oxide. And here you can put the all the chalcogen powder like sulfur, celerium, and tellurium. Then we are using some argon carrier gas like argon, and this is the hydrogen gas. So what will happen when the selenium will try to sublimate? So the carrier gas will take the selenium vapor, all this chalcogen vapor into this one, and this will react with the tungsten metal oxide powder, and it will form a desired substrate and deposit it on the substrate here. So what is the role of hydrogen here? So hydrogen will try to reduction. So MOO3 reduced to MO, and that MO will react with the sulfur to form MOH2 and deposit it on a desired substrate. So here you can see the growth profile and the characterization of the molybdenum diselenide, whatever prepared. So here you have the molybdenum oxide profile, and this is the selenium profile. And so one important point is that we have to time synchronization. At the time when it will evaporate, at the same time molybdenum oxide has to evaporate. And then this carrier gas will take over this one, the chalcogen vapor, and it will react with this one. And here you can see the typical characteristics of the Raman and as well the PL spectra of the molybdenum diselenide. Here we can see the around 1.55 eV. This is the theoretical predicted monolayer band gap of one layer MOEC2. And here you can see the optical microscopy images of the prepared material. Then we have different types of shape. You can see there is a triangular shape, some are hexagonal, some are some truncate shape. And the shape evolution also depends upon the different kinetics. And whatever, when you are taking this initial powder, by making sure all the temperature is same, temperature, flow rate, everything same. So if the ratio between the transition metal and the chalcogen, the powder, it will vary, so it will get different shape evolution. When it is equal to 1:2, you can get a perfect hexagon, because you can get the molybdenum terminated and the chalcogen terminated edge. You can see the equivalent 50-50. You can get a perfect hexagon. When the X ratio is greater than or equal to 2, you can get a triangle. So where the edge termination is X, and when you can get 1 less than or equal to 2 in this ratio, then you can get a inverted triangle. When it is the edge termination is molybdenum, the tungsten metal. So what we will do? So for the minimum surface energy, mostly this one, the either hexagonal or the triangle shape. Then we take this type of plex for the characterization. You can see the ACM images, and the FM image you can see there is a complete monolayer. Analytically you can calculate. So the thickness is around 0.7 to 0.8 nanometer. So this is the surface morphology of the different TMD using by CVD. We can have the molybdenum disulfide, tungsten disulfide, molybdenum diselenide, and tungsten diselenide, and so on. So coming to the heterostructure. So when you make two different monolayer material, then we get a heterostructure, and it is a hybrid material, and its functionality is completely different from that of the individual layers. So we can make lateral as well as the van der Waals heterostructure. You can make lateral lateral you can connect one over one and another. That means one material you can prepare, and then you take this material to the another CVD chamber. Then you will try to nucleate from this edge. Then you can have the lateral heterostructure. And similarly, what you do in the transfer processes, you can do the vertical heterostructure. You can first prepare one material, then using the weight transfer technique, you can transfer another material into that one, then you can get the vertical heterostructure. So you have the pool of a material, like you have the hexagon boron nitride, molybdenum diselenide, tungsten diselenide. Then you can make different type of heterostructure according to your own. But before designing an heterostructure, we should need some homework, because what type of application we are looking for. So, and accordingly, what type of heterostructure we are doing. Let's say if you are taking a graphene and TMD heterostructure, graphene mostly prepared on a metallic substrate, whereas the TMD grown on the insulating substrate. So in situ heterostructure is very, very difficult. So we have to go for the outer plane heterostructure or the van der Waals heterostructure. And if you can make the TMD heterostructure, so both we can do. We can go for a lateral heterostructure as well as you can go for the vertical heterostructure. And in a particular application is concerned, let's say if you want to get a tunnel field effect transistor, then you can make a metal in between a hexagon boron nitrate. So this type of heterostructure you make. So similarly, depending upon the application, we have to design and we have to prepare our heterostructure. So when you prepare the heterostructure, so two aspects is very important. One is the scientific curiosity, what is happening, what is the basic mechanism of this material, and to change the novel functionality, what is the change in the optical, electrical, and the electro-optical properties of this material. So here you can see a synthesis of the Van der Waals heterostructure. So generally, we prepare one MOEC2 on X can be selenium or sulfur on the sapphire substrate. Then you do the conventional graphene transfer process, like you can coat some few drop of PMMA on it. And then what you will do, you will ease the underlying sapphire substrate. Now the PMMA is holding this, what is called the MX2. And then we will transfer using a silicon oxide substrate, just like you catch the fish. So you can SiO2 substrate, you can take it and fish this material. And then you can clean the PMMA using the warm acetone. Now your design material is deposited on a silicon oxide substrate. So when you want to make a heterostructure, what you will do? So this process you do again and again, but instead of the silicon oxide substrate, you can take one fast TMD which is transferred on the SiO2 and then you try to fish it. Then you have the desired heterostructure. If you want to change the interlayer coupling between the layer, then you have the three type of transfer. So this is a three structure material. One is the WSC2, another hexagon boron nitrate, and this is the MOEC2. So similarly, all types of TMD based heterostructure you can make using this wet transfer technique. So when you rotate one over another, I told you earlier, so it in emerging a different field is called the twistronics, where the twist control electronics. So the degree of freedom is the twist, just you rotate one over another. And you can see that there is a diverse electronic property is changed, and also the diverse optical properties you will get. We can change in the band gap, spatial symmetry, interlayer coupling strength, exciton dynamics, phonon mode, charge transfer, everything will change, just a simple rotation of one layer with respect to the another. Here you can see I have rotated the molybdenum diselenide layer over the tungsten diselenide layer. Here the bottom layer is WSC2 and the top layer is MOEC2. So this is just like a 0 degree stacking, and this is a 60 degree, the highly symmetric stacking. And just then here I can rotate here 6 degree, 10 degree, 20 degree, and up to 56 you can see. So variable range from 0 to 60 degree I can rotate here. And this is the AFM image, one of the stack angle. You can see the bottom layer is around 0.7 and the top layer is around 0.8 nanometer. But when you do this rotation, because this is a weight transfer technique, so some residue and others may be trapped a little bit, then you do some post-annealing process, but still some localized wrinkle and that will be firm, we cannot be avoided. And another thing, the determination of angle is also, there will be some error, because sometimes the sharp is not, the edge is not perfectly sharp, and then we can get some 1 to 2 degree error in the angle measurement. And another thing is trick, if you have this, whatever I discussed earlier, this is about the plaques have similar dimension. But if you take plaques of dissimilar dimension, one is a larger plaque, another is the smaller plaque, then we a single domain, you can get all type of heterostructure. You can see, you can get 0 degree, you can get 60, and all the different angles we can get. This is the MOEC to WSC heterostructure. This is the WSC to on WSC heterostructure. So then we do the heterostructure, and then we do the photoluminescence as well as the Raman spectroscopy to probe this interlayer coupling between the heterostructure, twin dependent interlayer coupling. So when you take this type of heterostructure, this undergo a type 2 band alignment. In the type 2 band alignment, the valence band maxima belongs to one layer and the conduction band minima belongs to one layer. So when you shine on the light, so what will happen? The electron will go from valence band to the conduction band. Similarly, the electron will go to valence band to the conduction band. Due to the band offset, it will relax here. Similarly, role will relax here. This electron and hole, they will combine each other to form a new type of exciton called interlayer exciton. So mostly the interlayer exciton, this is electron hole pair belongs to the same layer. When in the case of interlayer exciton, electron and hole belongs to the different layer. So this is the initially the theoretically it was predicted, but the first time we demonstrated experimentally this one in the CVD flex. And here you can see the low frequency Raman mode. When the angle are close to 0 and 60 and close to 60 degree, you can see there is emergence of the shear mode. And when it is diverse from the high symmetry stacking configuration to the low symmetry, so misalignment, then you can see the layer can breathe. This is the layer breathing mode. And we can also, the layer frequency, so similar, you can say that low frequency mode are more sensitive to the interlayer stacking as well as the coupling. And then we take the PL spectroscopy. So very interesting result. You can see this is the monolayer MOEC2 and this is the monolayer WEC2. The intensity falls drastically because some of the electron and hole, they will try to contribute in this direction. So in the monolayer case, whatever we are getting in the intensity, this is plotted by reducing 1 by 10 times. And this is the twisted heterostructure. You can see the intensity is reducing drastically. Then there is a change because it is going from direct to indirect band gap. This is the nature of this material. It is going from one layer to the bilayer system. And then you can see there is emergence of the interlayer exciton. When the stacking angle are very close to 0 and 60 degree, you can see the interlayer intensity is maximum. Then it reduces at intermediate angle. Here you can see here. So there is exciton generation, then there is relaxation, that is a radiative recombination, then you can form this interlayer exciton, and that is more sensitive to the twist angle. But what are the important applications of this interlayer exciton? Because the normal exciton lifetime is in the order of picosecond, but this interlayer exciton, the lifetime is the order of nanosecond. So this large exciton lifetime is good for the Waal electronics application because all these materials are Waal-based material. So there are multiple Waal maxima and minima at the different Brilliant zone symmetric point. So you can use this material for the Waal electronics application. And then what we do, you try to understand what is happening there. So if you rotate one over another, you can see very beautiful Mori pattern you can get at some selected angles. You can see the periodicity is there. So you can say instead of whatever the lattice constant of a monolayer, when you make a twisted bilayer or some particular angle, then you can say this beautiful pattern called the Mori pattern. Then you can have the superlattice. So using this superlattice parameter, we can calculate all the band structure, density of states and everything. And when you talk about the TMD, because in the graphene, it is a hexagonal structure, the 6-fold symmetry, maximum periodicity is 30 degree. But when you talk about the TMD, the periodicity is 60 degree. You can get some commensurate and some incommensurate structure. And some commensurate structure, we try to calculate the electronic band structure using the DFT. And here you can see, we rotate the angle. This is the top view and this is the side view. And from this calculation, what we see, the interlayer separation is the crucial role. When the case of highly symmetric stacking configuration, like 0 and 60 degree, you can see the interlayer separation at 3.39 and 3.38 angstrom. That's why we get this interlayer exciton peak, and then it gradually decreases. And some intermediate angle, you can see it increases. That's why the coupling strength is very low. That's why there is no effective charge transfer. We are not getting the interlayer exciton. And then another technique also, by simply doing the PL imaging technique, you can see here. So some of the angle which is close to 60 degree and 0 degree, you can see the drastically change. The PL intensity go down and here, and some intermediate angle, it is not substantial. Okay, so for using the PL imaging technique also, we can able to identify what is the coupling strength between the different layers. And this is one material, another heterostructure like MOEC2 and WS2 heterostructure where the conduction band is degenerate. In that, so another 5 minutes? Yeah. Okay.
Another 5 minutes to go.
Okay, I will complete it. So the conduction band is degenerate. So in that case, there is a band hybridization occurs. Due to the band hybridization, the conduction band will split, and then we can have some hybridized exciton. So in this case, you can see when the stacking angle is very close to high symmetric stacking configuration 1.8, we can get this hybridization exciton HX1, HX2 and other things. And that the theoretically it is predicted. And this is experimental, we have verified using the PL reflection contrast spectroscopy as well as the PL spectroscopy. But on the other angle, we cannot get this hybridized exciton. So this was published in Nature in 2019, and this was a collaboration work with Professor Novasalov. And then here, recently we have done an MOEC to MOEC2 Van der Waals heterostructure. Here you can see the lattice constant is a little different. So when there is a change in the lattice constant, so you can get some delta factor. So in that case, what will happen? Some Mori pattern also you have 0 and 60 degree. Some Mori pattern is formed due to the incommensurateness of this lattice constant. And here you can see when we are making an heterostructure, we can get the two interlayer peak. Apart from this AX term, this is the trion peak. Sometimes some extra electron getting added to electron hole pair, and it's called the trion. So this is two interlayer low energy peak. One is IX1 and another is IX2. And that also we have demonstrated using the theoretical colleagues in ISC. And this was recently published in the PRB. And here we can see this is IX1, this is the interlayer exciton momentum direct exciton. So we can see from the absorption spectra from the oscillator strength, but momentum indirect we cannot see in the absorption spectra theoretically, but here you can see. And the most challenging things in this field is the how to control the twist angle. So here you can see in a recent paper in graphene, using some pulse growth technique, so they can able to try control the twist angle. So this is, you can see from 30 to 3 degree, 30 degree, different stacking angle you can control. So what we are doing, we are preparing material and then we are artificially, we are going to stacking. So this is a random technique. We cannot control at a particular angle we want to get. So using this, by following this paper, we tried our initial work in the CVD on bilayer MOS2. So here we can see this is a perfectly zero stacking and perfectly 60 degree stacking we are getting. So now we are working how to control in situ to get the different twist angle from 0 to 60 degree configuration. And so these are the new platforms in the twistronics. So you can have the electrical control of the charge density. You can apply the pressure control of the interlayer coupling. We can use some external law like magnetic field, temperature, voltage, current, and other technology related to the device fabrication. So there are endless possibility of the MOEC materials, and we can have the different discovery of a novel quantum phase material, and so on. And these are the summary selected publication in this area. So we have also writing one review now about the twistronics, because this is the right time to write a review. And these are the funding agencies, and these are all students who are working here. And finally, thanks all of you for your kind attention.
Well, very nice to see this diverse variety of van der Waals, heterostructures, and a lot of possibilities. Quite a bit of these things also require computational support.
Yeah.
And good quality synthetic methodologies along with quality measurements. And all of these require a good amount of instrumentation to be built specifically for the purpose. So it is all very nice. And so I would only like to ask the following question that, well, at this point in time, it is mostly towards understanding new physics.
Yeah.
What emerges out of this. And that is very nice. But the way the twistronics works, or the van der Waals heterostructures work, with all its difficulties in reproducibility, high dependence on the kind of synthetic methodology, where will this go to? And what you should focus on to get something out from it for society?
So thank you. So yeah, this is a valid question. So mostly the reproducibility and other things are the major issue, because when you talk about the CVD, so it is not a very straightforward method to prepare this material. The humidity, all the temperature, pressure, all the conditions are very, very crucial. So one has to be very expertise in growing this material. Okay, so that is one of the challenging technique in the CVD growth. So mostly we start with some exfoliated flakes when you are doing a new material you want to carry. And when it little bit stabilized, and then we can try over the CVD growth of this particular material, depending upon the availability, and the contamination issue also in the CVD is also very, very important. So we have to take care. We are taking this protocol how to avoid any contamination issue and other things in the CVD. And in situ control and everything, that is much more challenging. So you are working it out how to control in situ, or this stacking angle of different heterobilayer as well as the homobilayer system. And I hope with respect to the time, it will be stabilized and will carry in the proper direction. Yeah.
Thank you.
Yeah.
All right, let us take other questions.
So another interesting work we are doing, I have not shared, that is the blue energy, renewable energy using this 2D membrane, making nanopore and the mesopore in this 2D membrane and maintaining the salinity gradient. Okay, so
Right.
we are working on that one. Yeah.
Sure, there is some work going on in our laboratory also.
Yeah, I heard about that.
In the larger context of these, obviously, the right kind of application is a key
Yes.
point, especially in this kind of very fragile materials. I wanted to ask you, well, van der Waals heterostructures are interesting. A and B both are, 2D. But are there are interesting materials where you can probably combine with 1D and 2D material.
Yes, yeah. People are, we are also combining 2D and 3D. Some do ZNO with MOEC we have combined. We get some lasing effect. Okay, the random laser. Yeah, that also we are starting some work. I have not put it here. We are working on that aspect also. Yeah.
Very nice. Okay, so let us move on. Thank you very much, Professor.
Thank you, sir. Yeah.
So we will go to the last talk of today because Pallav, who was supposed to give the fourth one, he is unwell today, and so we will close with Abhijit Deshpande's lecture today. Abhijit, again, you will have that 20 minutes warning, and go ahead. Abhijit is going to talk to us on complex fluids, viscoelasticity from bulk behavior, etc., etc. Or he is into complex fluids and viscoelasticity.
Yeah, is my screen
yes,
visible?
absolutely.
Okay. I wanted to switch my video off, but anyway, maybe I'll start, and in case there is an issue, then I'll come back and switch the video off.
Yeah. Sure.
So thank you for this opportunity. This is a pleasure to talk about some of our work, which is in the field of looking at complex fluids, specifically polymeric materials, and at times particulate systems, colloidal as well as non-colloidal. And the main focus is on the mechanical response. And so the smaller length scales, unlike what Pramod talked about, is still in micron, maybe nanometers at times, but definitely higher because of mechanical interest. So the overall outline of what I'm going to do is initially start with some overview of what we've been doing over the years, just to place in context the different types of materials that we try to probe for their viscoelastic response. And then I'll try to give few examples from literature, current literature.
Kindly mute your microphones.
Yeah. And also talk about then finally about where we are looking at smaller length scale behavior with a couple of systems which currently we are working on are industrially relevant samples. So in terms of the overview of research activities, the main theme of a lot of our work has been related to looking at aggregated system, gel systems, and try to look at their mechanical response under controlled flow condition, which is what rheometry is all about. And the applications of the material systems which we have worked on tends to be as fuel cell membrane. It could be a biomaterial or a modification of viscosity, and the complex materials that we generally work with could be mixture of two polymers, so polymer blends. They could be acidic polymers having a significant degree of ionization. Also working quite a bit with supramolecular gels, where small molecules form gels in a suitable solvent. And of late, we've also been working on natural polymers, both proteins as well as polysaccharides. And key emphasis in our work is also to look at the microscopic picture, and looking at that microscopic picture, try to understand the overall rheological response. And rheological response is basically done using a standard technique where you take the material between two plates and you shear under controlled conditions and then try to analyze the stress strain response. These are some common geometries which all of you are probably familiar with in terms of viscosity measurement. Given that the materials which are polymeric also show both dissipative and energy storage response, we can analyze not just viscosity, but modulus and therefore viscoelastic response of these materials. And the key to doing that effectively is to use variety of protocols. So for example, you can apply a shear which is oscillating. You can do squeezing of the material. And today's talk is more focused on thin gap, where the dimension of the material. So for example, here the particles are similar order of magnitude as the gap which is being used to shear the material. And the general interest in our group has been looking at several types of assemblies, which could be molecular or based on particle systems. And a three-dimensional network is a key thing. So that's why gel-like response in many of them. So we are always looking at transition from liquid to solid-like, how reversible are these transitions. And naturally, these are very important for material preparation and processing. And we could have a cross-linked system in case of a polymer. It could be a physical entanglement. We could have clustering of molecules due to hydrophobic, hydrophilic, or ionic interactions. Particle assemblies are possible. Crystallization, which will form as hard domains in otherwise a flexible polymeric system, can also work as network forming agents. And we also have worked with surfactant systems. So just to complete the overview, I just sort of summarize few of the material system just to highlight the diversity of materials which could be investigated using rheology. And more importantly, we could connect to the microstructure of these material system. So you could have a cross-linking system, which is a polymer. This is what is used in diapers, and it's a super absorbent polymer along with a filler. I'll just give a couple of examples and then move on in the interest of time. But this slide summarizes several material systems that we have worked on. For example, an ionic cross-linked polymer, which is cross-linked with sulfosuccinic acid. These could be used as polyelectrolytes. We've also worked on wax crystal network, where wax crystallizes out in several different morphologies, needle-like or spherical spherulite crystals, and then how their behavior is when the crystals impinge on each other and form a gel-like network in which the solvent or the oil is trapped. A lot of work related to supramolecular networks. Recently, we also have been working on polysaccharides. Pectin is a plant polysaccharide, and it's gel due to calcium cross-linking. And so this gives you an idea of the broad range of materials in which microstructure forms the key in terms of defining the overall response. Just to quickly run through one example and the type of work that we do. So this is, maybe I'll just go back to the previous slide just to make a remark that a lot of this work is in collaboration with colleagues from the Institute, Suzy, Basa, and Ramnathan in our department, then several others from the Institute also. And this particular work is in collaboration with Dr. Ganesh from CLRI, whose group works on amino acid-based supramolecular gelators. And so you can see that this kind of a gelator system has hydrogen bonding interaction sites. There's a pi system, and there is also a hydrophobic moiety. And so there is self-assembly when you put these in different types of solvents, and they form chiral systems. And these helices can assembled together in terms of bundles and leading to basically a gel. And our role in this collaboration has been to try to correlate gels which are formed under different conditions, or gels which are formed by changing some of the moieties on the gelator system. What role do they play, and why do we get gels in some case, or why do we get gels with more strength, and so on. And we do this partly by also looking at not just small deformation behavior of the material, but deform them to significant extent. And in this case, for example, there is a network. The network will lead to breakage and reformation during the mechanical deformation. And so we look at this in very large strains. So here, for example, it's about 1,000 and 100, which are the strains used. And we generally tend to model it using, so in this case, it's a network model which talks about how junction points are broken or junction points are formed, and what is the strength of these junction points to deformation, so that it gives us an understanding of why certain gelators work better than the others. And so with this overview of set of materials and kind of tools that we use in our rheological investigations, I'll spend the next few minutes trying to highlight going to smaller scales and what are different examples where others are also working in this area. So just to start out with, when we look at a simple fluid and let's say water and the flow of water, we are looking at basically that up to 1 nanometer length scale, viscosity is defined. So only when we go below that length scale, specific molecular structure of water and its interactions with the surface, if it's bounded within surface, all of those start playing a role. And water can have both viscous dissipative component, implying viscosity, but it also can have elastic contributions due to several structural readjustments that can happen in the presence of a mechanical force in such confinement. It also has several other consequences. And so for water, given the time scales involved, which are 10 to the power minus 12 seconds, 1 nanometer is a length scale which is good enough in terms of 1 nanometer and higher for us to assume bulk behavior. But when we look at the complex materials that I have given you the examples of, we are looking at macromolecules and particles which span several length scales and several time scales. And this is because if you look at the physicochemical interactions and the mechanisms which are responsible for the mechanical response of these materials are quite diverse. I mean, you have the flexibility of the molecule, the rotation, vibration, stretching, bending and torsion of a molecule. We of course have several interactions, whether it's electrostatic or van der Waals or hydrophilic interactions. Given that polymer chains are entangled with each other, that introduces another set of interactions, and therefore architecture of these macromolecules plays a very important role in terms of determining the overall response. And of course, if you have a solvated system, then interactions with solvent itself also play a key role. Looking at a multi-phase or a particulate system also, again, we have these plethora of interactions in terms of hydrogen bonding or steric interactions, repulsions between particles, and again, interactions with the solvent. And consequently, the time scales involved in these materials range from microseconds to all the way to hours and days also at times. And so they always end up giving us both viscous dissipative response as well as energy storage elastic response. And I'll go through now a few of these examples from recent literature. This is polymer melt under 2D confinement. And what you can see is a coil-like molecule, which generally would sort of tend to be the conformation of a macromolecule in 3D ends up being a more extended molecule. And so this molecule, which is otherwise flexible in a 3D sense, due to confinement, ends up behaving like a rod-like or at least a semi-flexible macromolecule. So therefore, the response of such 2D systems to mechanical response is quite varied. And in fact, over the last 10-20 years, there have been significant experiments which sometimes show both effects in terms of increase in viscosity and decrease in viscosity. And a lot of that has to do with in which way do the conformations of the polymer change when you go from 3D to a more confined system. One other example that I wanted to sort of show where the properties at small scale are important is, let's say, if we look at plant cell wall, how let's say plant cell wall is effective in leading to the growth of a plant, and what are the mechanical phenomena which makes it possible for plants to either gauge its environment or change with respect to the environment or split and grow. And if you look at plant cell wall, it has pectin and then cellulose, microfibrils, and of course one can characterize these in bulk. By bulk, I would mean, let's say, something like we can make a film of these which is 1 mm, 1 millimeter. But of course, given the micron size and given the plant cell wall dimension and the dimension of macromolecules and the microfibrils, it's important to look at the mechanical response at small scale. And so in this particular work, for example, local deformation using AFM was used. And this has become quite a common technique in the last 10 years or so to look at small scale mechanical response of many of these materials. The other example I have is from a plankton movement. These are species under marine environment which basically go along with the current. And what's interesting about these plankton is near the body itself, surrounding the body, there will be polymers which are basically extracellular polymers, and they modify the overall viscous environment that this plankton sees when it swims around. And these are again some recent measurements of viscosity as a function of distance from a wall that the plankton is. So if plankton is very far away, so 10 microns away from the wall, its relative viscosity is basically the environment viscosity, water viscosity is just the same. So the plankton is pretty much moving around in water with viscosity, which is the bulk viscosity. But as it approaches a wall, you can see that there is an increase, and this increase is of course predicted for even an inert material like glass. So you can see that even glass has a slightly higher glass also experiences a higher viscosity, but because of the polymer which are surrounding the plankton, the viscosity can be very high. And so naturally, if you want to really measure mechanical response of what this plankton sees when it approaches a solid surface where it might adsorb or it might form a colony, it might aggregate and so on, we really need to understand what's the microscopic, rheological environment. And in this case, for example, what was done was using video microscopy, you can put some probe particles and then look at the motion of those probe particles and then try to back calculate the viscosity, the micro viscosity environment. You could also do these things with more active control of those particles using techniques such as optical tweezers. There are few examples which I wanted to end before I want to just speak about a couple of specific examples from our own work. You could have polymers in pore spaces which are confined. You could have very soft microgel dispersions. because particles, when I spoke about, they are basically silica or titania or hard particles, but you could have a cross-linked hydrogel particles, which itself undergoes shrinking depending on pH, temperature, or confinement. An interesting example would be, let's say, in terms of eating, and the feel of chocolate in the mouth is related to its viscosity, but again, not the bulk viscosity, because as chewing proceeds, what really we perceive and we feel the richness of the chocolate or how it feels in the mouth is very much related to, you know, the viscosity in a very thin film, where the cocoa and the sugar and fat has been mixed with the aqueous environment in the mouth, and the thinnest possible film is what determines what is our perception of how good or how rich does a chocolate feel. So therefore, there has been a lot of attempt to look at traditional rheology, but measure the viscosity or other properties in very, very thin films. So I'll just talk about two such examples, which are both based on industrial applications. And again, just to remind you, when I say thin gap rheology, what we mean is the content, the structural elements, whether it's macromolecular or particle, are a similar order of magnitude as the gap in which we are trying to look at shearing of these materials, as opposed to bulk rheology, where each element is much smaller, 10 times, usually as a thumb rule, 10 times smaller than the gap. And so the context for us has been based on coating application. This is based on Saint Gobain work, and then solid propellants, which are basically metal particles along with in a polymeric resin, which is for DRDO. And the challenges in both of these cases are as follows: that coating by definition is very small thickness, and also very high shear rates have to be used. In case of solid propellants, the loadings are extremely high. We are talking about 70–80% solids. And so anytime you try to measure viscosity or any other flow property, secondary flows make it very difficult. And so in DRDO, for instance, they are not able to correlate how solid propellant behaves in while making the rocket propellant motor versus its viscosity that is measured in the lab. And so can thin gap be used to extend the shear rate, and you can measure the properties. So we'll start with that propellant system, and you can see that the particle size is around 300 microns. It's a very heterogeneous system. 10 micron aluminum particles, and then 5 to 300 micron the potassium chloride, which is used as a surrogate oxidizer in our case. And you can see that the gap that we have used also is 0.5. And if you compare, so you basically have 300 micron particles in a 0.5 mm gap. So the question also is that what are we measuring? What is the property that we measure, and what is the significance of it? Because otherwise, when we say viscosity, it's a material property, and under different circumstances also, if we measure, it's going to remain the same. But now we are probing the material at those length scales, where each different length scale gives us a different response. So this material, which sort of shows a fluid-like response, shows an yield stress when you go to lower gaps. The other material that we have worked on is hollow glass sphere. It's a coating system in polyurethane. And here again, what I'm showing you is viscosity as a function of stress. And when we have high stress, the viscosity is constant. But when you approach lower stress, the viscosity seems to go to infinite. So again, there is a jamming, what's called a jamming transition as gap decreases. And so more and more, many of these materials, this data is of course for 50 micron gaps, but if we test the material at high gaps, we don't see such jamming. So the jamming is influenced by gap, and it's influenced by the concentration also. So one of the things we try to do in these kind of cases is also do particle tracking and actually look at what's happening to some of these individual particles and how are they moving. And so if you look at, let's say, two different gaps, so you can see that this is a trace of those particles based on which we can measure the velocity. And if you look at particle velocity as a function of angular velocity, the velocity which we are doing the shearing, in fact, they are independent of concentration as well as gap. So really, there is no jamming per se. It's not that particles have stopped moving, but the way the particle crowding, effective particle crowding, it leads to a higher mechanical stress. But there is no getting together, clump formation or aggregation of these particles to a jam state. So this is something we are still working on. And so I'd like to close by saying that, so we work on rheology of polymeric and network systems. Hopefully, I've been able to give you some idea of which way do we do some of these things. I also try to say that smaller length scales and looking at rheology viscoelasticity is becoming more and more important because we have large number of questions of scientific and application interest. And so I closed with just giving a couple of examples of our recent work on industrially relevant systems. And in closing, of course, I would like to say that, there are several such material systems which still remain to be probed at thin gaps or at lower length scales. And the other key thing is to measure other characteristics along with rheology, be it microscopy, be it a dielectric response. It could be any other spectroscopic response also, so that we know what's happening when we are doing shearing. And of course, also look at complementary tools such as AFM or other nano indentations and so on to complement our understanding of the rheology. So with that, I'll stop. I thank you again, and I'll be happy to answer any questions that you have.
Very nice, Abhijit. I didn't give you a warning because I realized that it is, it'll be closed and within the limits.
Yeah.
So as you said, structure is a key factor in rheology, and conformation, molecular, specific interactions, all of these. But molecules themselves or materials themselves are changing in the recent past. There are lots of variety in that.
Yeah.
For example, a given kind of particle, the size is changing. Material is the same, but the size is changing.
Yeah.
Or a polymer is the same, but the size is changing. All of these.
Yeah.
So, to what extent can rheology see those finer molecular changes? Is there a limit? Are we at the limits today? Those are interesting concerns that a chemist would have.
Yeah, no, so I think the key thing remains is whatever underlying structure has to have a mechanical consequence. So some of the materials that you mentioned, for example, could lead to a different maybe electronic response, but not necessarily a mechanical response. But there are several materials, and supramolecular gels, for example, is an interesting one small modification at a molecular scale leads to very drastic changes in its mechanical response. And so for such systems, it becomes very valuable to look at rheology as a probe.
So are there some pointers, for a chemist, for a who makes materials to look at? Where will rheology give us an additional handle?
Yeah, so one example that I can see from I have not worked on these is this, let's say, conducting polymers. And so you have a molecular scale feature, then there is a mesoscopic feature, and then the bulk response. And the electronic response, of course, depends on both molecular and mesoscopic, and so does mechanical. So by doing mechanical probing of these materials, we can get complementary information and try to arrive at a better understanding, so that we can, even if, let's say, it's a conducting polymer and eventual goal is to have a better conductivity, we can do that by also looking at mechanical spectroscopy, so to speak. And that's being done actually. So a lot of times when we are doing, let's say, the spin coating or any other operations as to what kind of mesoscopic patterns are formed, that we probe using rheology and then try to arrive at the best mesoscopic structure that can give you a good electronic conductivity.
Say, the previous talk, Pramod was talking about, a small twist changes the electronic transport property so significantly that twistronics. Now, here is another case where again there is a twist or something that is happening, or a shear that is happening, but a large change has to be manifested. So where are those? Obviously, you mentioned about, well, small change in structure, but big change in mechanical property. How would materials fellow look at it? That way, this area, both the areas will be enhanced.
Right. No, so I think dialogue is needed in terms of trying to take it forward. Within rheology also, there is a lot more emphasis on now trying to capture from a modeling point of view what's called a micro-macro approach, so that you go from molecular length scale all the way to bulk response. And within rheology also, we try to integrate spectroscopy or other techniques to get better information to what's happening to molecules during shear. And so those are the directions in which then it becomes more useful for, like you're saying, chemists and rheologists to talk.
So Abhijit, when something is shearing, what is your understanding? Today, this shear is happening between, let us say, immiscible liquids. So there is a liquid layer between these two. So now you shear. Are you shearing at a molecularly thin what is moving? Is it one liquid layer over the other at a molecular length scale, or several tens of molecules?
No, so from the let me. So actually, when you do shear, there is a relative velocity between any two molecular layers, and only thing is by doing bulk rheology, we cannot really talk about the response which is at the molecular scale. So given the overall fluid mechanical theories and all of those which are at continuum scale, we cannot, but the underlying physics which is happening, it's happening at the molecular levels itself. And so current understanding of what is the magnitude of viscosity, let's say when you're shearing, comes from several molecular dynamic simulations which are looking at one molecule layer shearing over the other molecule layer.
That is where spectroscopy and others
can play a role. To complement.
Okay,
so that's why we have to do bulk rheology, molecular simulations, and spectroscopy to really complete the picture.
Good. Colleagues, so let's take other questions.
Can I ask one question?
Go ahead.
So Abhijit, so you're saying about viscosity at a very small length scale. So what is the effect of boundary layer phenomena? If you are like the distance is very small between the two sliding surfaces, and when you have a particle, mixture like a liquid and a solid particle, do you have like a boundary layer which is only liquid, or there is like a segregation? Have you observed anything like that?
So that does happen. So even if you, let's say you have a suspension, depending on the interaction between the liquid and the surface, bounding surface, or the particles and the bounding surface, you may end up with a very thin layer of fluid which keeps the solid particles away. Or you might have reverse, where the particles adsorb on the bounding surface and actually don't move at all, and fluid flows around them. So both these possibilities are there. And so when you are doing bulk rheology, what happens is these effects at the surfaces are immaterial, because the overall stresses are being governed by a material which is basically continuum. But when you do this at very thin gaps, then these effects that you're talking
Yeah,
about play
yeah.
a much more important role. Yeah.
Yeah.
So therefore, you have to then characterize these interfacial interactions a lot more carefully before you can then say, you know, what's the viscosity and why is it. So basically, there will be a difference between viscosity at bulk and viscosity at these thin gaps, and what's the reason for it. And as I said, viscosities higher or lower than the bulk have been reported. And so it again depends on a specific mechanism that you can really understand that specific material system.
Thanks.
Yeah.
All right. Are there other questions,
Okay.
colleagues?
Yeah, Professor Abhijit, this is Pramod here. Yeah.
Hi. Yeah.
Yeah. So I want to one thing know that a general question
Yeah.
regarding the mechanical responses of this small scale system. So how will you measure? What are the challenges by measuring? AFM, I know this is one non-destructive technique you can do. So let's say if you do the fracture toughness or hardness or other mechanical aspects. So what are the challenges of measurement?
Right.
Yeah. Mm-hmm.
So the first thing is related to the a model or a mechanism of how the tip or the surface that you're trying to probe, what are the interactions, right? And the other thing is what is the sort of response of the surface. So for example, it's harder to probe some of the materials that I talked about because they are softer materials. So when you're trying to probe it using a tip, the material itself can deform quite a bit, and then therefore the force which is being used on a tip is difficult to immediately get some properties out. But for metallic or ceramic materials, it becomes it's a one order of magnitude less complicated because their response is small deformation, and also it's largely in the elastic domain. The key feature, of course, will depend on what's the resolution that you can get through the AFM tip. That's the only smallest possible. So there, depending on what probe you use, you can go to slightly smaller or larger dimensions.
All right.
Okay, thank you.
Yeah. Just a quick point, one point I wanted to make. There is a Tesla turbine concept which makes uses of this viscosity fluid flowing between two surfaces, you know, that, and it has very high efficiency and so on. Maybe some of your studies can you know, maybe usefully there also. Yeah.
So there is a renewed, though I have not worked on it, but there's a renewed interest on that Tesla turbine. Given that now we can probe microscopically, you know, what's happening during flow, which is bounded by very thin gaps. Yes, there is a renewed interest in Tesla turbine also.
All right, then it was an interesting talk, and we should close this. And thank you very much, Abhijit. Thank you all the speakers. So let us meet next month with another list of speakers. I'm sorry that Pallab could not participate, and let us hope that he recovers fast. Thank you very much. Bye.
Thank you.
Thank you. Thank you.
Bye.